Hi, this is Eric Grelke. Today we're going to talk about distillation and trying to review distillation for binary and multi-component systems. This is going to give us an idea of how we will change our approach to solving distillation problems when we go to a multi-component system. We will have then a separate discussion of how to set up the multi-component distillation system. We're also going to talk a little bit about economic analysis of the whole system as well. So let's start with doing a distillation review. The reference that I'm talking with respect to is Cedar and Henley, which is a separations process principles book, and chapter 7 is on binary distillation, and chapter 9 is on multi-component distillation. What I've done is I have reduced and simplified what is needed for this class out of these two chapters. Here is a typical distillation column. Here I have stages. The top stage, and I'm showing you a ChemCAD simulation picture now. The top stage is labeled as 1. The bottom stage is labeled as N, so the stage numbers increase from top down to the bottom. The feed is going in someplace in the middle, and we'll denote the mole fraction of the light key as Z in the feed. At the very top, the overhead vapor is going to a total condenser. Everything is condensed. It goes to a reflux drum where you separate out the liquid. There's a pump which is not shown. It provides pressure to drive distillate out of the process and reflux back into the process. The pressure of the feed and the pressure of the reflux need to be slightly higher than the pressure of the column in order to get the liquid back in. The top part of the column above the feed stage is the rectifying section. We are removing the light key in this section. Below the feed stage is the stripping section. We are increasing the concentration of the heavy key here. Down at the bottom, we'll use a partial reboiler. This doesn't condense everything. It only condenses some of the material, and actually reboils some of the material. So there is some vapor going up here. There is a bottom product which is taken off there. The light key and the in both the distillate and the bottoms are shown as marked. ChemCAD and other process simulators will solve multi-component distillation systems and other separation systems using K values. K values can be based on equations of state or activity coefficients. If we have hydrocarbon streams and light gas mixtures, we often use equations of state. If we have other systems which are very non-ideal, we may use activity coefficient. There are a number of appropriate forms for the K value, all the way from the ideal solution, Raoult's law, to the Poynting correction, which corrects Raoult's law for both a non-ideal thermodynamics and pressure. And then for a number of simple stripping operations, for example, if we are removing hydrocarbons from a liquid stream and things are very dilute except for the liquid stream, we will use Henry's law coefficients. So this is all very helpful, I think. In general, what we're trying to do in a distillation column is we are trying to separate the light key and the heavy key. Any material which volatilizes at temperatures lower than the light key will appear in the top, usually, and any component which volatilizes at temperatures higher than the bottom key will appear in the bottoms, usually. This is a very effective separation technique, but it is energy intensive. In the future, we probably will be using more separation techniques that are not as energy intensive. As an example, in 1976, 40 years ago, we used 2 quads of energy for distillation in the United States. The total consumption of electricity in the United States at that time was about 90 quads. So we used a significant portion of the energy just for distillation, at 3% at the time. There are a number of different kinds of condensers. I thought we would do those, review those very quickly. On the left, A is a total condenser. Everything is being condensed. The liquid then goes to the reflex drum that we talked about before, and then we split it, some going back to the column and some being used as a product. Another way to do this is to use a partial condenser. Do not condense everything. Send some liquid back to the column, but have a vapor distillate feed. This would be going to another unit operations, probably. And then C shows you a mixed condenser where you do a partial condenser. You really separate the liquid and you send some of the liquid back as reflex and then take off a liquid distillate. You would do this kind of thing. You would have two different products, a vapor and a liquid, if you could get a very good separation with the vapor. And that would usually mean it has a very high volatility, even at the conditions in the partial condenser. Here are some reboilers. I've got 3 shown here. Up at the top is a typical reboiler kettle. What happens here is the bottoms come off the column. They're fed into the shell side of the coil. Steam is coming into and out of these tubes. There's a pass to the left, there's a pass to the right. This is split in the middle. Steam vapor comes in the top. Steam condensate liquid comes out the bottom. What this particular design does is it puts a weir which is above the steam coils, the steam tubes, so that all the tubes are always covered by liquid. This helps give a more uniform use of the tubes and make sure every tube is being used to vaporize the stream from the bottoms. The vapor is then sent back up the column, to the column as the vapor feed, and then the liquid is taken off as a bottom product. An alternative is a vertical thermal siphon. When the bottoms fills up to a specific point, it starts to feed into the bottom of this vertically mounted heat exchanger. So there's material in the tube. Steam enters in the shell side, goes in the top, the condensate of the steam, liquid condensate comes out the bottom. And most of the tube surface will be in the liquid phase. There'll be some nucleate boiling at the top of the tubes, generating the vapor, which is going to go up the column here. An alternative is to take the liquid not off the bottom of the column, but off the downcomer from the nth tray, the bottom tray in the column. Take that, put that into the reboiler. Same kind of situation here. We use steam, the vapor, and all of this is now vapor boiled off and sent up the column. So we've reviewed condensers and reboilers. Remember that there are a number of specifications, and you have to have enough specifications for the column to match the number of equations. Here is a list of equations for a column with a total condenser. There will be other equations that you use for a partial condenser, other sets of specifications. You notice you have a lot of specifications, which means you need lots of equations to solve the problem numerically. This reminds you of the McCabe-Thiele diagram that you've used in separations class before. This is the plot of the light key, and we show the mole fraction of the light key going from 0 to 1. So this is pure heavy key, this is pure light key. This would be appearing in the top of the column, this would be appearing at the bottom of the column. And then this is the mole fraction of the more volatile component in the vapor phase. So this heavy curve is the equilibrium curve for vapor-liquid equilibrium of the light key in the mixture of the solvent. And we are just considering two components now, the light key and the heavy key. So we can plot the equations that are going on in the rectifying section and the stripping section very easily. The bottom product is coming out, let's say, at 14% of the volatile component or the light key. The top is coming out at about 87% of the light key. We've drawn an operating line for the rectifying section. We've drawn a stripping line for the stripping section. This is the Q line, which describes what's happening to the feed. If the Q line were vertical, we would be sending in a saturated vapor. This is not quite a saturated vapor. Excuse me, this will be a saturated liquid. Saturated vapor would be a horizontal line. So this feed to the column is partially vapor, but mostly liquid. Again, if it were all vapor, it would be a horizontal line, and if it were all liquid, it would be a vertical line. And then this shows you a blow up of what would happen if you just had a stripping section. And it shows the operating line down at the bottom of the column and the equilibrium curve. This reminds you of the feed quality for the binary system. Again, if the line from the feed point is vertical, you're feeding saturated liquid. If it's subcooled, you're feeding a line which has got a positive slope. When you're feeding saturated vapor, the line would be horizontal. Superheated vapor, the line is got a the slope as you see here. So the thermal condition of the feed makes a big difference of what's happening around the feed tray. Normally, for efficiency, you would like to put in some mixture of liquid and vapor. That is not always possible. It is usually more economical to do the liquid vapor mixture in the feed. So there's some things to remember about the feed condition to your column. The feed pressure has to be greater than the pressure in the column as it's coming in. So you will often have a valve there. The valve may actually give you a partial vaporization of the feed, which is what you would typically want anyway. The temperature of the feed doesn't necessarily equal the temperature on the feed tray. The multi-component distillation equations will solve for what the temperature really is. Usually, however, you will avoid a subcooled liquid and you will avoid a superheated vapor and try to supply a partially vaporized feed. This can be done in a number of ways. The most common way is to use energy recycle and use either the distillate or the bottom stream to heat up incoming feed that may not be as a saturated vapor at the feed condition. There's a trade-off between the reflux ratio, the reflux from the condenser at the top of the column, and the height of the column. Here is an example of a calculation for a binary distillation of hydrocarbons. On the left is the reflux divided by the minimum reflux. So this is the minimum reflux to do the separation. If we ran the column at those conditions, we would have an infinite number of stages. The column, however, would have the lowest diameter. You have an idea of what the reboiler duty and the condenser duty would be. We can calculate the cooling water cost and the steam costs. And then when we sum these together, that plus the equipment cost on a yearly basis, that'll show you what it costs to run this thing for a year. As we increase the reflux ratio, we can reduce the number of stages. This reduces the cost of the equipment. However, it increases the cost of the cooling water because we need more cooling water now that we are condensing more, and we need more steam because we are boiling more up in the reboiler. So that's the type of trade-off that we have. Increasing the reflux ratio gives you smaller equipment, but it's at the cost of more utilities. And so there's always a balance. And one of the things that we'll do when we're looking at the economics template is to look at how to do the balance. Here's an example of an annualized cost. The data from that table were plotted here versus the reflux ratio. So here's reflux ratio and here's the annualized cost. Someplace down in here, like right about there, is the optimum reflux ratio because This is the minimum total annualized cost. As we increase the reflex ratio, the cost is going up because we are using more utilities. If we go the other direction, the cost goes up because we use much, much bigger equipment. Someplace down in here is where we would like to operate the column. So this is for a typical separation. If we have a very difficult separation where the volatility of the key components are less than 1.5, then this plot can look quite different. When we're choosing a place to operate the column, we can do a simple plot like this to get us very close to an optimized condition. And that's one of the things we're going to be doing in the first problem. Okay, you are familiar with the FUG method, which is the Fensky-Underwood-Gilliland equation set. It has been generalized for multi-component systems. It's based on light and heavy keys. And generally, even though we use this to get started, we prefer simulation to actually depending on the FUG method. Here is an example of how it's employed. This is step by step. You identify the split that you want in the key components. You estimate the split of the non-keys. You determine column pressure and the type of condenser you want. Look at the feed. You flash it at the column condition to figure out what the condition of the feed would be. Calculate the minimum theoretical stages using the Fensky equation. Use the Fensky again to calculate splits. Make sure that when we calculate the splits, we now get a condenser flash and a reboiler system condition that's similar to what we thought we had. Once we have this balance going, then we can calculate the minimum reflex ratio using Underwood, calculate theoretical stages using Gilliland, estimate the feed location, and then calculate the condenser and reboiler duties. So this is a multi-component way to estimate the column, but it's best used with ideal liquids. If you have a non-ideal liquids, this will not work particularly well. And here's some examples for this particular case. Here are some things that will make it difficult to use this FUG calculation system on multi-component problems. When you're near reflex ratios that are near the minimum, the distribution of non-key components is often difficult to calculate. And so you really need to do tray by tray energy, thermodynamic, and energy and equilibrium balances to figure out what's going on. What people have found is that the rigorous simulations are better indicators of the column performance. Typically, if you don't know anything else, you would choose a reflex ratio of 1.3. That could get you started, but the best thing is to do the rigorous simulation. So that's a very brief summary of looking at the binary distillation problem, converting it to a multi-component distillation problem, estimating the keys, estimating the non-keys, and getting close to what the split should be, the number of stages, minimum reflex, etc. What we'll find out is it's actually better to do that estimate if you can, but quickly move to a rigorous simulation and solve the problem rigorously from the beginning.